Welcome to Session 4 of Digital Basics, Math by Logic. As we always do, we begin by reviewing the answers from last session's exercises. We're asked to do some binary arithmetic. The first one turns out to be pretty easy as there are no carries. We can confirm the result by converting the binary values to decimal. The second problem includes 3 carries. Again, converting to decimal, we can confirm the result. For the fourth problem, we're expanding the 4-bit binary field to 8 bits, and we have a lot of carries. For this one, we'll convert the binary values first to hex, and then, converting the hex values to decimal, we find that we expect the answer to be 138. Converting the answer to hex and then to decimal, we find that they match. For the last problem, we're presented with hex values to start, and we convert these to binary, since it's binary addition that we're exercising. We do the binary addition and then convert that back to hex. Now, as promised at the end of the last session, we'll see how binary arithmetic can be done with logic gates. Say we're given 2 values, value 1, which is hex 5, and value 2, which is hex A, and we're asked to add them together. We can convert them to binary, and we see that with this combination of numbers, there are no carries, and for this specific case, we could simply use 4 OR gates. But what if we just want to add, say, 1 and 1? Would just OR gates work? Of course not, since we know that the answer should be 2, but with just OR gates, we'd get only a 1. Let's look at all the possible combinations for adding the LS bit, for both the carry bit and the sum bit, the one that becomes the LS bit of the final answer. The carry bit is easy, since it is only 1 when both the added bits are 1, and that's an obvious AND function. And what about the sum bit? Neither one simple OR nor AND gate would work, since neither one works for all the combinations. Notice, though, that when the bits to be added are the same, the sum bit is 0. And when the bits to be added are different, the sum bit is 1. Here's a gate combination that's active only when the inputs are opposite of each other. To understand this, we'll look at all the combinations of the inputs. This is a common method of analyzing gate operation, and we call it a truth table. When both inputs are low, the 2 AND gates block them. When in_1 is low and in_2 is high, the upper AND gate is active. Similarly, when in1 is high and in2 is low, the lower AND gate is active. And finally, when both inputs are high, the inverted inputs of the AND gates are blocking. Notice that the output is active only when the inputs are different. We call this an XOR function, and this is the gate symbol. Returning to the original scenario, we see that we can implement the sum bit with the new XOR gate. And since we've already determined that the carry can be implemented with a simple AND gate, we're done with the LS bit position. And so we move on to the next bit position, where we'll change the operands, the inputs value 1 and value 2, both to 3. With the carry bit, we now have 3 ones to add together. Once again, we'll use a truth table, this time with 8 combinations, since we have 3 operand bits. So, how do we arrange gates to implement this table? We'll look at the main sum output first. A simple approach is to use AND gates to decode all those combinations that produce an asserted output, and then OR those together, like so. We can do the same with the carry out, like so. Trying another approach, we notice that for all but one combination, the carry out is the inverse, the opposite or inverted version of the sum output. So we could use the gate configuration we just created for the main sum output and invert it, which leaves us with the first and last combination. We can decode the first one, all zeros, and block or gate off the inverted main sum output. So, for that combination, all zeros in, we force the carry out to 0, which leaves us with just the last combination, an all ones input. Here, we decode that combination, all ones, with another AND gate and OR that through. This is all very clever, and it's worth taking the time to understand what we did. But if we count, we find that this uses just about the same number of gates as the earlier simple decode approach. So far, we've developed gate combinations that add the first 2 LS bits, shown here as signal vector bits, like so. But, of course, the next bit positions, all the ones after the LS position, work the same way, with each carry bit passed on to the next position. Let's take the gates that we developed to implement the second bit position and represent them with a symbol box that we can call a bit adder. Now watch. We can use this generic bit adder for each bit position, even the LS bit. We tie the LS bit position carry input to 0, which means that some gates for that box are not used. But that's okay, gates are cheap. And what about the MS bits carry out? Watch again. We can group all 4 bit adders together as another symbol that we can call a nibble adder. A nibble refers to 4 bits, just as a byte refers to 8 bits. And we can now concatenate nibble adders together to add larger vector signals, tying each carry out to the next carry in, like we did within the nibble adder. This is an extremely important concept, well worth taking time to absorb. We refer to this sort of groups consisting of a number of subgroups as a hierarchical design. One last point. As in the nibble counter, what do we do with the hierarchical carry-out? We could call this an overflow flag, since our 16-bit output signal, sum, is not large enough to accommodate this condition. And the exercises for this session.